All right, welcome. Today we're going to jump into a super powerful tool, something straight out of a top consultant's playbook, the P-chart. It's the perfect method for getting a grip on quality when your data isn't some complex measurement, but just a simple yes or no. Let's dive right in.
So think about it. You've got a production line, right? It's cranking out thousands of items every single day. Some are going to be perfect, and, well, some just aren't. It's a simple pass or fail. It's good or it's bad. You can't just average pass and fail, can you? So how in the world do you track your overall quality? And more importantly, how do you spot a problem before it gets out of hand? This is the exact reason the P-chart was invented.
So here's our game plan. We're going to tackle this just like a real consulting project. First, we'll nail down the problem we're trying to solve. Then, we'll introduce our tool, the P-chart. After that, we'll walk through exactly how to build one. We'll even do a little deep dive on a critical difference between the classroom and the real world, before we finally put it all to use and learn how to read the results. It's a really clear, logical path.
Okay, so let's set the stage here. When you're measuring something like the weight of a product or maybe the length of a part, you have a whole toolbox of charts and graphs you can use. But here's the thing, all those tools, they completely fall apart when you're just counting stuff, when your data is just one of two things. This really gets to the heart of it. You've got two fundamentally different types of data in quality control. Over on one side, you have variable data. This is anything you can actually measure on a scale, length, weight, temperature. For that, you use things like X-bar and R-charts. But then you've got this other world, attribute data. This is stuff you count. Does it work? Yes or no? Is it defective? Yes or no? This kind of data needs a totally different approach, and that's exactly where our P-chart comes in.
So now that we know the problem, what's the fix? Well, it's a purpose-built solution called the P-chart. And yep, that P stands for proportion.
So what is it really? At its heart, it's just a visual way to track the proportion or the percentage of bad parts you're making over time. Instead of tracking a specific measurement, you're tracking a rate, the failure rate. It's a subtle shift in thinking, but that's what makes it so incredibly powerful for this kind of data. So where do you actually use this thing? Well, first, think of it as an early warning system. It'll catch a sudden spike in defects immediately. Second, it lets you monitor if your process is stable and consistent day to day. Third, it's perfect for proving that a change you made, like installing a new machine, actually improved things. And maybe the best part, it's designed to handle situations where your sample sizes are all over the place, which, let's be honest, happens all the time in the real world. All right, we've talked about the what and the why. Now it's time to get into the how. We're going to get into the nitty-gritty now, the actual framework for turning a bunch of raw numbers into real, actionable insight.
Okay, but before we touch a single number, we have to lay down some ground rules. You see, for a P-chart to give you anything useful, you've got to make sure these four things are true. Basically, it has to be a level playing field. Every item has to have the same chance of being bad, there's no kind of past, one bad apple can't cause another, and you've got to test everything the exact same way. Break these rules, and honestly, your chart is just garbage in, garbage out.
So here it is, the 6-step roadmap. It's super logical. First, you just collect your data in batches. Then, for each little batch, you figure out the percentage of defects. That's your P. After that, you average all those percentages together to get your overall average, your P-bar. That becomes the center line on your chart. Now, step 4 is the big one. You calculate your upper and lower control limits. Think of these as the guardrails for your process. Finally, you just plot everything on the chart and stand back to see if any of your data points went outside the guardrails.
Okay, now for something really interesting. A bit of an insider tip, actually. When you start calculating those control limits, you're going to hit a fork in the road. And this is one of those subtle things that really separates someone who's just read the textbook from someone who's actually done this out in the field.
So, on the one hand, you've got the formula they teach you for the exam. It uses something called n-bar, which is the average sample size, to calculate just one set of control limits for the whole chart. It's a shortcut to make test questions simpler. But out here in the real world, things are messier. Your sample sizes might change every day. So the right way to do it, the more accurate way, is to use n sub I, the individual sample size for each and every point. This means your control limits actually wiggle up and down a bit, giving you a much more honest picture of what's going on.
And look, don't just take my word for it. The author of our source material, Ted Hessing, calls this out directly. He literally says they teach the simpler version because, well, that's what's on the exam. This is such a great example of why context is everything. So the takeaway is simple. For the test, use the average. For your job, you got to use the individual number every time if you want real answers.
All right, theory's great, but let's make this real.
We're going to walk through a quick case study from the material to see how this all comes together. This is where we see all this stuff in action. So here's the setup. We have a company making tubes, and they've collected data for 20 days. Notice how the sample size changes from day to day. Okay, so we crunch all those numbers, and we get our overall average defect rate, our p-bar, which comes out to about 1.5%. This is our baseline. It's the historical average for this process, and it's going to be the center line on our control chart.
Okay, now we're going to use that real-world formula we just talked about. For day 13, where the sample size was 1,150, we calculate a specific upper control limit just for that day. When you run the numbers, you get an upper control limit of about 2.13%. Think of this number as a line in the sand. Anything above it for day 13 is a major statistical red flag.
And here it is, the moment of truth. We look at the actual data from day 13, and the defect proportion was about 2.17%. So we take our actual number and we put it up against our limit. And boom, it went over. 2.17% is higher than our 2.13% limit. It crossed the line.
And that's it. That's the finding. The process is officially out of statistical control. Now, that doesn't mean the factory's on fire. It just means something unusual, a special cause, happened on day 13 that pushed the defect rate way beyond what's normal. The P-chart did exactly what it was supposed to do. It raised its hand and said, "Hey, something weird happened right here. Go look."
And that really brings us to the most important part, doesn't it? See, the chart is amazing at telling you that a problem exists, and even when it happened, but it has no idea why. Was it a bad shipment of raw material? Did a machine fall out of calibration? Was there a new person working that day? The P-chart is the tool that kicks off the investigation. The real detective work, finding the root cause, that starts right now. So, where would you begin to look?